Recording in progress.
Oh no, how do I change the speaker? Can you spell Ted's name for me? It should be on that paper back there. Maybe. Oh, it may be cut off. What about the back side?
It's such a long title.
Is it cut off on the other side too?
Okay, yeah, that's not. SWANSEGAR.
All right.
Swansegar. Awesome.
Thank you.
One, two, three, four, five.
Teams files, and then I'll let you. So after I'll give you some extra time, like in soccer. Yeah, give you a little extra time. Penalties, you know. Yeah, of course. And then we'll, if you want to use those mics when we're answering questions, unless you're up here, make sure you do that so that everyone can hear. When if any of your team here is answering questions towards the end, and they're not up here, use one of those mics. So, yeah, and I can help you with that. How are we looking?
I think I went through.
So can we, slide with this?
Yes, arrow key.
Okay.
Okay, and back arrow key goes back, right? Yeah,
Do you guys need a laser for
it's laying on top if you need it. That advance?
Okay. Does that advance too?
Yes,
Yeah.
yes. So if you want to hold that,
Whichever way you like to go.
I'm gonna guess going up. Okay. Good morning, everyone. Thanks for joining us for our 10:50 session. Advanced traffic signal performance measures and connected vehicle technology. My name is Ryan Hughes. I'm a project engineer with Clark Dietz in Lexington. I'm going to introduce most of the team that we have up here. Jarrod is not here, correct? Okay, all right. We'll start with Joe Carter. Joe graduated from the University of Kentucky with a bachelor's in civil engineering. He's a traffic engineer for the Kentucky Transportation Cabinet and has 10 years experience working with the System Operations Branch in the Division of Traffic. He specializes in traffic signal timing and communications, along with the art of signal timing coordination. Joe is the liaison for districts 1, 6, 10, and 11, and has retimed over 250 traffic signals in his career. Ezekiel Goodwin began his career with the Kentucky Transportation Cabinet in the fall of 2010 and began working in the Division of Structural Design. After passing his PE exam in 2014, he transferred to the Division of Traffic Systems Operation Branch in 2015. In traffic, he has been involved in developing timing, troubleshooting, research and development, and providing support for the district personnel as it relates to the operation of traffic signals. He's also responsible for the maintenance of the in-house programs used to maintain KYTC's older traffic signal controllers and systems. As of late, his primary function has been converting the older 170 controllers to the new 2070 ATC traffic controllers, as well as assisting in troubleshooting for the districts as they install these new controllers across the state. Telma Lightfoot was a civil engineering scholarship student and graduated from Kentucky State University and the University of Kentucky. She spent a majority of her full-time career working for the Kentucky Transportation Cabinet in the Division of Traffic Operations, focusing on signal timing and signal coordination throughout the state. She assisted in the development and training of several employees and consultants on various traffic-related topics. Telma currently manages the statewide traffic engineering services contract and is district liaison in the systems operation branch for several districts. And then our final speaker is going to be Shane McKenzie, but she's going to do an introduction for herself. So please welcome our team today.
Good morning. It's good to see you all. It's good to be with you. I have to say that Jarrod would be standing up here today to introduce this project. He has been project manager on the project and is definitely a part of our project team that has made it successful. And this team, I'm excited to tee up this for them to explain all the details about the project. My background is actually not from Kentucky. I'm from the West Coast. And so I come by way of my first internship was from the Port of Portland, and I added red lines to as-built on a design build project that allowed the airport to expand its parking structure, canopy, the elevated roadway, and terminal expansion. So then I moved to the city of Battleground where I lived. From there, I started out as a technician, moved up to the assistant city engineer before moving with my family. And thanks to cheap airline flights, I was able to commute back and forth from Chicago, working for C.H. Hill. Some of you might know them. They're now Jacobs. But all of that happened before I started working in the Division of Planning for the Kentucky Transportation Cabinet in 2013. And now my role is the Connected and Automated Vehicles Technology Lead. So now we get to start the time, right? This is a packed presentation. I'm very excited about it. These guys are phenomenal. You need to get to know them and you need to talk to them. So here we go. Here are the project details. This was an aid demonstration funded project, federally funded project. So the It's advanced innovation or accelerating innovation deployment demonstration is what that stands for. So it was 80-20 funding. The basics, essentials of the project is to implement ATSPMs, automated traffic signal performance measures, that's a mouthful, and connected and automated vehicle technology in Madison County on Kentucky 876 in US 25 and in Warren County on US 231. In a minute, you're going to hear a lot about the corridor details and the background and characteristics from Telma. This project basically involves installation of equipment to implement the ATSPMs and CBT technology. And the main components you're going to hear from Zeke all about these components: advanced detection, connected vehicle radios, module for controller system configuration, validation, which for some of these things we haven't done before. The integration part of this is very new to us. So the project led it in November 2019, and the completion date originally was supposed to be August 2020. So that changed, primarily due to COVID, but other reasons you'll find out about. The reason this project is so important to Kentucky is it has safety implications, congestion implications. You're going to hear a lot about those from Joe and the benefits. And also the other portion of this, not only the benefits for the public, but benefits for us on the backside to learn how to deal with how to make this stuff work. It's got all kinds of it's got open source software, it's got integration, it's all kinds of things. And then there was a challenge that we met that was a nationwide challenge. You hear a little bit about that. And it definitely has some potential environmental impacts that we could mitigate with ATSPMs. So with that, I'm going to ask Telma to come up here, and she's so awesome. This whole team is awesome, and you're going to love to hear all about this.
As Shane mentioned, 2 corridors were selected for this project. US 231 in Bowling Green, which consists of Scottsville Road and Campbell Lane, and Kentucky 876 and US 25 in Richmond, the bypass. Several factors played a part in our decision of making these 2 corridors our proof of concept and an introduction to ATSPMs. Each corridor has unique features, as you can see, and similar. As for Richmond, the southern part of Kentucky 876 is an urban area, whereas the northern section is more rural, which allows for uncoordinated signals, speeds of 55 miles per hour, and intersections are spaced further apart. The Richmond bypass also has on the urban section entrances for Eastern Kentucky University and the hospital, which allows for a different flow of traffic. For Bowling Green has a frontage road that runs parallel across Scottsville Road, and it also has preemption with the city, with the Bowling Green City Fire Department. As you'll notice, both of these corridors have several challenges and concerns that represent why we chose them. Congestion and spacing of the intersections and spacing of the frontage road for Bowling Green was also another key point. Spillback, which is when your left turn storage is not sufficient to hold your left turn cues and spills back into the through lane, preventing them to proceed through the intersection. We also had split failures and progression. In Richmond, we also have varying traffic with the university for football games, graduations, things like that. And on Scottsville Road, when you look at some of those challenges, even though it's a benefit that we have the preemption for the fire department, those signals are coordinated and synchronized along the corridor. So as when the preemption is activated for the fire department, that gets those signals out of sync and it affects your progression along the corridor. So Zeke will now talk about equipment upgrades.
All right. Now, as Telma just said, I'm going to be talking about the equipment that we not only upgraded, also we had to add a few pieces to this project. Now, first off, I'm going to be talking about the controller. The controller is the brain of the traffic signal. It's what tells it what to do, when to do, and pretty much how to do it. And we started out with a 170. Now that we've had this for the last about 30 years, it's 1970s technology. Basically, there's a 6-digit LCD display in the front with a 16-digit keypad. You have to know codes. You have to know basically exactly what you're doing in order to program any tagging. Now, our predecessor, Glenn Anderson, actually developed a program called TransFab. And what we do with this is we use it to program the controller in a very graphical fashion. This is basically what's allowed us to use this for the last 30 years. Now, about 5 years ago, we discovered that we were going to start to have problems updating or not updating, but replacing and finding new equipment for the 170s. So we went on a search and we decided to change to the 2070 ATC controller. This controller on the front panel has an 8-line 40-character LCD display. Along with the 16-digit keypad, it has an additional 12 keys with arrows and escape keys. And it also serves up a web page if you're connected to it through an Ethernet connection. We use cellular routers to communicate. And you have a little taste of what the max time page looks like. Moving on, we have had to upgrade our detection. Now, I kind of have to go back to discuss what detection is like in the state of Kentucky. For about 95+% of the signals in Kentucky, we use what's called semi-actuated. Now, what this means is that the side streets and the left turns have detection. However, the main line does not. Now, you might think, well, the main line is the most important street, so that could be problematic. But what we do is we put this on recall, so now no matter what, there's always a call on the specs. Now, for the ATSPM side of the project, we needed this detection. So we had to come up with a way to fill that gap. And we decided to go with radar detection. Radar detection is very unintrusive. Basically, you can install it without having to spend too much time on the roadway. I think it took about a week on each corridor to install all of the radar detection and fill all the gaps. Here's an actual video of one of the radars in Bowling Green. You can see the blue rectangles moving are the vehicles. The green rectangles are the detection zones. And when they turn red, the radar sends a signal to the controller to tell it that there's a vehicle in that detection zone to put the detection in. Next, this one was a little more of an extra benefit. We didn't really have to do this for the project, but in 2 locations, we decided to install what we call an ITS cabinet or a serial cabinet. The biggest benefit as far as this project went was they have 16 output channels. The old cabinets only have 12 output channels. Now, an output channel is 3 outputs. Typically, it's red, yellow, green for most cases, which you do have heads, which are walk and don't walk, but that's a different story. So you've got, in the old cabinet, you've actually got 36 outputs versus the new cabinet, you now have 48 total basic lights that you can turn on, off and on. Now, if you look at the front, the left side of your screen, you'll see the 332 Caltrans cabinet that does have a 170 in it. Now, I will make a note, you can use the 2070 in the old cabinet. They work perfectly fine, and that's what, is when we're switching over. But it's considerably different than the serial cabinet here on the right side of the screen. But the real key difference is how the controller communicates with the cabinet. On the left there, you're going to see the back of the 2070, which actually has both outputs. In the middle, you're going to see a C1 connector. That's an analog connector. Every pin controls one output. But on the serial connector, it's basically a 25-pin printer cable. And it communicates to the controller through a digital format or machine code, if you will. Now, moving on, this is some new technology that was added to the locations. And this is the DSRC roadside unit. Now, this is a kind of a conglomerate of devices, but it's actually, well, we call it the RSU for roadside unit. But it basically consists of a piece of software that resides on the controller, sends data through a PoE injector, which is just power over Ethernet. It applies power to an Ethernet cable that then sends that all up to the DSRC radio. And then the DSRC radio sends a signal out to vehicles. Real quick, here is just a laid out picture of what these devices look like. It's laying on the ground. From left to right, you have the radio. Then in the middle, you have an Omni antenna, and then the PoE injector. I didn't picture the GPS antenna or Ethernet cable here, but if you look right behind that white antenna, which is the primary antenna, is a Garmin GPS antenna mounted on top of a car. Now, this piece of equipment is the onboard unit, or OBU. Now, if you look in this is like a Pelican or a suitcase. You'll notice that you still have the radio and you still have a PoE injector, which is the same as what goes on the pole. However, you'll also, if you look, you'll see that's a Raspberry Pi and then a cellular modem. And the Raspberry Pi serves up to a tablet that then displays the information from the intersection or controller. And at this point, I'm going to hand it over to Telma to discuss a brief history of the ATSPM project.
You might be asking yourself still at this point, what is ATSPMs and why do I care? How's it going to help me get to work, to the grocery store, to my kids' school, wherever? How's it going to benefit me? Well, the 2070 ATC controller is one of the key components that allows us to collect this information because it collects high resolution data. About 5 years ago or so, I heard an analogy, and I've heard it several times, on how the best way of explaining what ATSPMs are. So picture a fitness tracker on your wrist. What is it? It's an accelerometer that collects data every second. Well, that data is then sent to an application that analyzes the data and will tell you how many miles you've traveled, how many floors you've gone up, your calories burned, etc. So ATSPMs, this process is the same. What it does is it takes the signal status and the detector status, sends that to the controller at a less than tenth of a second, and then that information is sent to a server and the software. The software then does the analysis and creates reports. This concept of ATSPM started about 20 years ago with Indiana Department of Transportation personnel wondering, there's data collected from a traffic signal. How can we put this into usable information, usable data? So vendors, consultants, academics, and government agencies met and had this discussion. What can we do? What are we getting? How can we put it out? And they also wanted to make sure that it was vendor neutral and make sure it could be scalable to all agencies. I was also fortunate to be a part of an NCHRP study, which came up with guidelines of how agencies could implement ATSPMs. Around that time, Everyday Counts, EDC 4 came out, and their initiative was, one of their initiatives was ATSPMs. Everyday Counts is a program that promotes innovation in innovation with that is proven but not widely used, and wants it also to be on a quick timeline. So at that time, FHWA sent out a survey. And if you look at this, at the map and at the chart, in January of 2017, about 11 states were in a demonstration for institutionalized state of ATSPMs. They were doing it, they were in the process studying it. If you notice, Kentucky is in a development state. We were still looking at equipment, personnel, funding. How could we do it? What did we need to do? By the end of 2018, over half of the country moved up at least one level, if not more, and started implementing and doing some form of development into ATSPMs. And you'll notice Kentucky is now in the demonstration stage. Joe will now come up and talk about the benefits of ATSPMs.
ATSPM benefits. ATSPMs provide a more proactive approach to optimizing signal timing along corridors and also individual traffic signals. The 10th of a second data stream of detector inputs and phase output offers better data supported engineering decisions. This is a continuous field data collection process. It's 24/7. It's like having a traffic engineer or a traffic technician at all of your traffic signals collecting field data. ATSPMs also provides improved safety through better mainline traffic flow and also more adequate side street or minor movement service time. There's also a public facing application that's actually what's pictured here of our application. And what this provides is it's a web address that anyone from the public can pull up a signal that they may have issue with and identify whether or not that signal does have a problem. So before I get into ATSPMs and how we're using them and how they're used, I first want to talk about traditional signal timing. Traditional signal timing depended on trigger events to kickstart any timing adjustments. And that was in the form of public feedback. We'll still have public feedback, I'm sure, on our traffic signals. ATSPM is not going to eliminate that, but we'll be able to more easily identify them and they'll be more quickly addressed. At KYTC, we did 3-year corridor reviews of our traffic signals, and through our consultant contractors or our central office staff. With ATSPM, we'll be able to monitor our systems more effectively and be able to maintain them at a higher quality. All right, the traditional signal timing corridor method. This is this is the process for optimizing our signal corridors. As you can see here, this is a pretty labor-intensive activity. It's detailed but lengthy. The data collection process alone can take one engineer, possibly 2 engineers that drive into the corridor, collecting, doing 12-hour days, collecting and doing multiple days a week, collecting data in the form of split counts, GPS, and also traffic pattern observations. So I first want to talk about how ATSPMs are used. Oh, I do want to go back. Oh, with ATSPMs, we'll be able to do a lot of the modeling and a lot of the timing adjustments using like instantaneously through the reports instead of going through this entire process. Sorry about that. Okay, so I do want to talk about an ATSPM case study. This was actually just done a couple of weeks ago. The district received phone calls that they were having trouble at a particular signal. And so this was at a school, and the feedback was that it was taking too many cycles. The parents were dropping their kids off in the morning, and it was taking too many cycles for them to clear the intersection. And then when they came to pick their kids up in the afternoon, it was still taking too many cycles for them to clear the intersection. So we were kind of missing quite a bit there. So here, the district contacted me. We pulled up an ATSPM report. This is referred to as a split monitor. Now, I do want to mention this isn't one of our aid intersections, but this just gives you an idea of how this works. What split monitor does, this is actually the approach of the claim. And so it's phase 4. And the x-axis is your study period, and the y-axis is the service time for the approach. That red line that you see throughout that moves around, that's the allotted time that we give them throughout the day. And so the first issue that I want to talk about is in the AM. As you can see, there's a collection of blue dots. Oh, each one of these dots is the service time throughout the day. I guess I mentioned that. The collection of blue dots on the red line here, that is the approach maxing out to its allotted time. And as you can see, that's about an hour. So that did seem excessive. So we ended up giving them additional time. The PM, this was a similar situation. We still got our collection of blue dots there on your right side. But here the solution was a little bit different. We tried to give them the allotted time that they wanted. If you see that large hump in the up top there, but we were just a bit outside. Apparently there was a change in schedule at the school. The school's now leaving about a half hour later. So here we didn't just give them more time. We just adjusted the schedule to reflect their change in schedule. And so this is what the outcome ended up being. We reduced the service time, the morning issue from 1 hour to 15 minutes. And then we reduced the PM issue to just a few cycles. So this took us like 10 minutes to complete, to come up with this solution, put it out there. We looked at the reports the next day and this is what we saw. If this was a traditional approach, this would have taken us 8 to 12 hours to be able to identify the problem, make the changes in the timing, observe those changes. So ATSPM is truly a game changer, as Shane would say. And then this particular graph is on our aid corridor. This is a Kentucky 876 at Kroger. This is in Richmond. And this is data coming from our server application. And so what this one, this is the Purdue coordination diagram. This is a pretty famous ATSPM report. This is demonstrating the arrivals of vehicles as they approach the intersection through advanced detection. And so this is typically used for signals that are coordinated, hence the name, where the platoons along the corridor are controlled through their timing plans. And so if you see the moldy looking dots there, those are vehicle actuations approaching the signal. And then the lines on the graph are the phase outputs. So the green line is when the traffic signal turns green, and then the red orange line is when the green terminates. So here, kind of laid this out for you. Anything above the green line is vehicles arriving during green time, and anything below the green line is vehicles arriving during red. So I want to point out an additional thing on this particular graph. The first thing I noticed when I took a look at this report was the void of dots during green time on plan 30. Not an ideal situation. This means the signal's green and there's just no vehicles approaching it. It's referred to as starvation. And additionally, we've got another collection arriving on red here. So I see a potential here to adjust the timing to capture more of the vehicles arriving on red, and then hopefully eliminating that void in the green time. So I do want to mention a few other ATSPM reports. I don't have time to talk about all of these, but I just want to inform you that others do exist. And there's new ones being talked about being developed by UDOT, GDOT, and other agencies through FHWA. You just have to pick the right report for whatever issue that you have. And so the final thing I want to talk about is the FHA 2020 cost benefit analysis. The return on investment is another huge benefit to ATSPMs. The agencies that have been able to, fully commit and invest have gotten very good returns. The most modest one was Maricopa County. It had almost 3 times its cost in benefit, and then Lake County, Illinois had almost 13 times its benefit to cost. But what we hope, beyond the aid project, we hope to expand the network to provide, better service, throughout the state of Kentucky and better performance as well. So now we haven't been able to apply a lot of the principles to the aid project because of some of the challenges that Zeke is now going to talk about.
All right. Now, with anything, you're going to have challenges. That's a give and take. This did seem to have a little bit more than we were expecting at first, for sure. First off, personnel and manpower. Now, this is now at this point everywhere. It seems like across the world, but we've been having this issue a little bit longer than that. And it's something that we just have to work through. And in all honesty, as Joe was talking about, we're kind of hoping this actually reduces the amount of personnel and manpower that we need. But we still have to get things installed. We have to get things working. Secondarily, we're pulling in huge amounts of data with this. We're getting, I think, 1/10 of a second resolution. So it is just pouring in. Now, we got to figure out what we're going to do with this, how we're going to store it. We have to maintain equipment to manage and analyze this. So that's been, and this is something that we are not used to. We're used to small amounts of data and basically jumping in a controller and fixing a little problem. So, we're still trying to muddle through how we're going to do this. And as I'm going to discuss, we've had a whole lot of IT setbacks that have essentially, basically what happens is everything, we get it working as far as the ATSPM reports, and then we get a Windows update or a server update, and it quits working for a couple of weeks until we can figure out what or how to fix it. Now, I'm not saying COT or IT has anything to do with this. Quite the contrary, they have done everything they can. And I'm going to name her name by first name, Laura. She's been absolutely amazing in making this work. And in the long run, it all comes back to security. So to shorten this up, it basically, lost my train of thought. Basically, we have to keep the security going. There's too many threats out there in the world to just get rid of. We also have mainline detection. This was a success in this project. However, if we move forward with ATSPMs, that first example Joe showed you, if you notice, that was a side street, but that signal doesn't have mainline detection. So if he wanted to do the Purdue diagram, that wasn't there. So as we move forward, we're going to have to figure out how to get that implemented. The continued maintenance of all these systems, and that's most of everything I just listed. That's all there: staff, data storage, maintenance of the server and IT equipment, and the detection. And it's all long-term costs. Now, with the cost benefit, does that come out ahead? We think it does. But to sum up, the ATSPMs, they're not going anywhere. We are going to keep them. We're going to fight to keep them, even if this is an open source software. If we have to go buy an off-the-shelf solution, I think that will be in our best interest. As Joe said, there's too much savings. The data is so much more widespread. I can look at weeks and weeks instead of having to spend 3 days in the field, 10 hours a day, just collecting data. I can do that in 5 minutes. So all in all, we're going to do everything we can to keep the ATSPM. They're a very beneficial solution to our traffic problems. All right, and with that, I'm going to hand this over to Shane to discuss the DSRC installation.
Okay, I think we have 5 minutes. So I'm gonna go through this as quickly as I can so we can get to any questions you might have. And we think you will. So let's start with what are connected vehicle technologies. Think of it this way. If there was a emergency vehicle coming down the roadway, we apprehension in some of our locations now, right? The vehicle can get through the signalized intersection by preempting if the equipment is at the intersection. Think for a moment if we change that or use roadside units for this application or this purpose. It would work, it would be faster. But then add a layer. What if all the cars had the same technology on them? Could they then move out of the way? Could a message be in the car that says, hey, there's an emergency vehicle coming, you need to get out of the way? And then 3 cars ahead could say, that vehicle could say, hey, I'm stopping, you 3 cars back, you need to slow down so you don't hit me. What if that could happen? That's what this technology does. It's referred to as vehicle to infrastructure, vehicle to vehicle, and vehicle to everything communications, which is what the picture on the left pretty much represents. It's an ecosystem. The technology was developed in 1999, so it's been around for a while. That map on the left hand of the screen indicates the FCC licensing which is the foundation to this technology. It is a dedicated spectrum. It is low latency. It allows for a basic safety message to transmit over the air in 1/10 of a second. And it's transmitting data like speed, location, and trajectory. So imagine if all the vehicles had that technology on them. One of the very famous projects that first came out of this was in Ann Arbor, Michigan. That happened in 2011. So the FCC licensing started in 1999. It took them until 2011, 2012 timeframe to come up with the standards and to get the Society of Automotive Engineers and IEEE and all of those standards developers to wrap their head around this and come up with a standard for the roadside unit and the onboard unit. That first pilot included 5,000 vehicles, 45 intersections, and other roads that they equipped so that they could test different applications. One was curb speed warning. Some of them is red light violation warning, which is something that we can get to in this particular project. Out of that pilot, NHTSA analyzed all the data and determined that 80% of all vehicle-to-vehicle crashes that are unimpaired can be mitigated by this technology. So that really put this map on the left side in action. At that time, there were only a few states that had permits to use this technology. It wasn't very well known, it wasn't proven. That pilot tipped off the USDOT ITS Program Office initiative, which was the 3 major pilots for across the country. One's in Wyoming, one's in New York, and one's in Florida. All different applications. In Wyoming, they've got winter weather and snow blowing. So what they did with that project is got the equipment into trucks, because trucking is a major component of our economy. And so if you could put warnings in those trucks, it could definitely provide safety measures to them. The New York project was all about, they implemented 5,000 OBUs, and it was on a variety of fleets, and it was also, they have pedestrian applications because there's a very big pedestrian safety problem. And then in Florida, it actually had a network that used arterials. And the benefits that came out of that were with a pretty relatively small amount of vehicles. They saw big benefits just in speed harmonization. So it was these pilots took off, and then there was a SPAT challenge that came out in 2016 timeline. That came out at about the very same time that the US DOT, NHTSA was about ready to mandate this technology on all vehicles. That ended up not happening. It was stayed through executive orders from one administration to the other. But the SPAT challenge had already spread, and that's why this map looks so green now, is there were so many pilot projects in state, and the challenge was for all 50 states to get a signalized intersection corridor with 20 or so signalized intersections equipped by the year 2020. So now all of the DOTs are excited about this, right? And we have this technology. But this is one of the first times that the auto industry has been a cornerstone. This technology is important to them too. The safety benefit that people could gain from this is enormous. So now we're working to integrate the vehicle information with the roadside information. This is a big deal. We haven't had this in our systems before. In this particular application, and you heard from Zeke about this equipment, but this is kind of how the diagram looks. The RSUs are up on the signal pole. The controller's got software that's implemented into it, and it does that translation from the signal language to the vehicle language. This is what the hardware and software looks like. You saw this earlier, the roadside unit on the left, OBU on the right, and then the max time software and the heads-up display for the back office display is what that is, to be able to monitor the system and make sure it's all set up right. I think perhaps one of the most interesting parts of this project is how to integrate the system. FHWA came up with a mapping tool where you could map your lanes so that the technology could locate you within that lane. So it could pick you up when the radio was transmitting. So the radio transmits 360 degrees at a range of 900 feet. That's a range of more than any sensors on a vehicle today. So it's a pretty big deal. The GPS survey tool is something that they use to dial in the intersection geometry to get it as accurate as possible. And this is the application. This is the tablet that we used to verify that the RSUs were doing what they were supposed to be doing, that they actually achieved the range that they were supposed to achieve, that the manufacturer told us that they would. This particular application is a data application. It's really cool. And if there's time at the end, we will put that in so that you can see how it runs. And then the early potential benefits in Kentucky are that emergency response, that emergency application. If we can partner with our emergency folks to put some units on their vehicles and try it out on these corridors, see if we can see a benefit, that's what we want to do next. And the important piece to that is a security credential management system. Each one of those basic safety messages that are transferring would be attached with a certificate, like some of our software programs that we use today, right? So it's a pretty safe, closed system. That's what makes it so awesome. The other application that's important to us, we have our legislators passed a law in 2018 to allow commercial trucks to use this connected technology along with automated technology to be able to get closer together and gain the fuel efficiency to be able to draft. And that reason that works is that technology is fast enough to allow those electronic braking to happen between these vehicles. So we might do this again. We didn't want to complicate this. But pivots and challenges really quickly. Most of the time this project was managed virtually. Our team lead, that's our big team lead, but our project team lead was Jarrod Stanley, and he made sure we had team meetings every 2 weeks, and these are still going on. And this was great because you had an integrator that was in Kansas City, and we had all of our other people that were in other parts of the state and in Ohio. So we were able to, it was actually a pretty efficient way to manage a project. So it was pretty cool. The RSUs were delayed. Once they were installed, we had antenna issues, so those had to be replaced. The manufacturer had to come out from California to troubleshoot all of those issues. We have lots of head scratching with the back office part of it, how to get that map set up, how to get integration working. That was a big deal for us. It was a big deal for our integrator too. We were all learning about FHWA tool and all the back end things. Then right midstream in this project, FCC made a big pivot change by splitting up that very narrow bandwidth into they took quite a bit of away, more than half of it away. What's left is still suitable for the applications that we're talking about today. And so what that meant is, instead of having use of that full bandwidth, we had to move to the upper bandwidth, and that meant changing channels. So that was a pivot. We're still pivoting on that. And we knew about a capital project that would be online in the Bowling Green corridor. That actually did happen. And so we had to make some pivots on that and move the cabinet, reinstall software, hardware, do some integration adjustments. Okay, I think we're good. We're good. Here's where we go from here. This is the future of transportation. And if we're allowed questions.
Well, what we'll do, since we gave them a little bit of extra time and we've already gone over just a little bit, we'll thank them and then have them be available to mingle and ask questions afterwards. If you want to meet for lunch, certainly do so. And be sure to look on your conference app to submit evaluations. But first off, give a great thank you to our people. So feel free to leave for lunch, but we'll try and queue up their video as well, and you can come up front and mingle for questions if you'd like.
From the same friends.
Oh, wow. Good to see that.
Doing good.
It's been a long time, man.
Got my phone, ready. Charge.
Yeah.
I used to do more, but now I just.
I'm glad to see the watch.
Yes, yeah, I got it.
Oh, I thought we were talking about the.
Yeah.
Well, I'm a total, don't worry, that was part of the information that I was pulling in. Yes, yes. Yeah. I get, I'm a third.
Jay, what's up?
I got ice cream.
Any questions that make it look good? Makes sense?
Easy on them.
Y'all doing all right? Are you still?
Yeah. I don't have any permits, so.
Are you guys still? Well, I heard I lost half my crew, or your crew. And it sounds like the other two are leaving next year. My wife's late or something. Yeah, I've been meaning to call you guys, any ideas on placing them or?
And I was like,
There you go.
We'll go back.
Right now.
Yeah.
The guys that take credit, we'll just go from there. With best plan, unfortunately, we'll probably have to be like everybody else. I'm gonna do like Hero though. That's hourly measure that we've got. Yeah, try to screw us for. Maybe say, tell you, have on them all.
Yeah.
All.
Well, I mean,
It's pretty sweet.
That's cool.
Yeah, they're ahead of this, and you have to, you have to.
So we didn't do a lot of that, but then we're really putting that like that. So we're just like moving from, I think maybe just a little.
It's
Yeah, Yeah, thank you. We'll see you.
Yeah, I think so.
Thank you very much.
Yeah, great job. You all did fantastic. No, that was
Sorry we
great.
went so far.
That's okay.
Yeah, you're right.
Yeah, when we first like came up, we thought we had 50 minutes, so like we planned this for 50 minutes, and we had to like